Okay. So, Professor Rudra Ghatak is currently working as a professor with the Department of Electronics and Communication Engineering in IIT Agartala since 2013. He has more than 350 publications in various national or international journals and conferences. He has been recognized as an inventor in various patents, including US patents. His research interests include the domain of fractal antenna, metamaterials, application of evolutionary algorithms to electromagnetic optimization problems, RFID, computational electromagnetics, microwaves, millimeter wave passive and active circuit designs, and terahertz sensing and communication. Professor Ghatak was a recipient of Ursi Young Scientist Award in 2005. He also received support under the DST Young Scientist Scheme for the development of UWB radiating systems for imaging radar. He has served as a domain expert in various state public service commissions. He has also served as a reviewer for an NPTEL course on antennas. He has also served as a member of Technical Expert Committee for 6G proposals in the Ministry of Communications, Government of India. He is a member of the Board of Studies at UG and PG levels at various state and central universities. He is the founding Board of Studies expert member in the Electronics and Communication PG program at the University of Bardhaman. He is also serving as a research advisor to TCS Research in the domain of millimeter wave radio design and signal augmentation systems. So now I will request Professor Ghatak to start his presentation. Thank you very much.
Thank you, Dr. Kormukar and Professor Mujumdar, who are the coordinators of this course for the Atal FDP. In fact, the very purpose behind such kind of courses getting wide recognition, and the purpose behind the different topics being encouraged to be shared among the academic community with sometimes experts from industry too. The reason is it has some pedagogical view, and it has to little bit cater to the not only the fundamental teaching aspects, and also pave the way for the industry linked and industry oriented way of course deliberation, which is fast getting more and more inclusive in our entire academic curriculum. So let's start sharing, and for this purpose I thought that I should share something, some fundamental aspects of the antenna engineering so far as the this course is concerned, which it also have the pedagogical views. This is our department in the green campus of NIT Durgapur, and obviously in the spring there are a lot of flowering trees. It's a very beautiful campus. So it's a glimpse of the various labs and the facilities where our students and group members are working. And these are the group members. In fact, Dr. Kormukar also was a part of the research group which was contributing on antenna optimization. So that you can see the different domains, our contributions have been channelized in not only the antenna as well as the micro and high frequency circuits, some particularly for the automobile sector, some very fundamental researches coming up as some design guidelines for the upcoming researchers. And in all this particular a specific topic of energy harvesting has wide implications, where the design of a correct sensor, which is an EM sensor, is very important for the efficiency enhancement in RF energy harvesting. Though the entire course I saw that the schedule is very well distributed into different verticals which are important so far as the developing and building up circuits for RF energy harvesting. I would be dealing with the specific little bit topic on the fundamentals of radiating systems and what we look for in designing such radiating systems such that we can improve the efficacy in whichever applications we want to put that EM sensor. Now, in this case, I would revisit this particular para, which was put forward by Professor John D. Cross in his IEEE AP transactions in way back in 1985, which marked the 100 years for the Hodges experiments. So to celebrate that, that issue was published. So it mentions about the mankind's activities expanding into space and the need for antennas, which will be enhanced in an unprecedented degree. Obviously, this sentence is written way back in 1985, published in 1985. I think young researchers, my faculty colleagues who are part of this program, they can enrich upon this fact, the sentences, that how relevant it is and how it is becoming more and more involved with so many different application use cases. Perfect. So far, the RF and the microwave and the ever increasing use of frequencies. So obviously, the antenna, which has over more than 150 years of history, because starting from the way it was conceived to be a part of a wireless system, experimented within some floors of the room by Hertz. It started with the dipole and the invention of the loop antenna, but it moved forward beyond that. And obviously, with the simultaneous development of the oscillators, it had a tremendous implications in the overall development in the wireless communication paradigm. So I would nudge every reader to go through these highlights of antenna history, which was published in 1981. In antennas, spectral expansions always lead to innovation. So it all started with so small frequencies. Now, what were the frequencies? That is also very interesting, because in those early days, we didn't have any oscillators. And obviously, in the years of 1870s and 1880s, 1890s, when they were measuring or wanted to send a certain signal for wireless communication application, there were no vacuum tube devices either. Forget about the solid state devices. So in that domain, it was really interesting that spark gap generators and the early receivers also, such kind of a spark gap generator was a very, very important component for as a source of EM wave. So there was a high voltage spark, and the EMI from that was a low frequency. Now, how much low? So if we look back to the experiments of Marconi, so it was quite interesting that the frequencies were so low, were below some 400 megahertz. So at low frequencies, it was very difficult that the signals will be transmitted over longer distances. And that's the reason that the Cape Breton in Canada, where Marconi was stationed, and the other way, it was Poldhu Port in England, within which the transatlantic communication was being targeted. The experiments ran away for many years. So what happened? At initial phases, he was thinking that they should use, in this beautiful island of Cape Breton, they should use masts and towers, which was having aerials, and pump in a lot of power because the frequency was low, to transmit it over longer distances. But interestingly, this principle was not, which was following the laws of physics, because if you have a very low frequencies and it is obviously highly attenuated by galactic noise, ambient noise, so we have a very small window in which there is a low attenuation from the ambient noise. The signals are less attenuated in the range of somewhere 500 megahertz to 10 gigahertz. And you will see that most of the wireless communication, if you start from counting from 2G, 3G, 4G, 5G, everything, and the applications in IoT and specific applications for IoT to harvest energy in these particular wireless domains, these are all focused in the ranges from 500 megahertz to 10 gigahertz. Now, this particular frequency sets, you will see that they are least attenuated, so they can be transmitted over longer distances without impairment. Now, if we talk about the experiments of Marconi, so he chose a very low frequency and had a concept that will pump in a lot of power, but that didn't solve the problem. So he took the help of the Carl Ferdinand Brown, and then he suggested that if you just enhance the frequency, you need not pump in a lot of power, and you would be successful. And in one fine day, he was successful. And with his success, the Marconi's instruments were getting very much marketed by Marconi Instruments. And one of the ships, which was Titanic, which generally purchased that, but it was unfortunate that it was Titanic who purchased. The other ship which had such kind of a Marconi wireless system was the Carpathia. It was far away and it took long time. But the Postmaster General at that time, he credited it to Marconi that because of him, whatever the number of people may be saved is due because of him. So that was the general viewpoint in which we see the initial developments in the wireless systems and the role of different frequencies in transmission. And the other one, which was really, it has not materialized as a 5G Advanced and 5G Pro, which we yet to see it realized to have a 5G dongle at 60 gigahertz. But the experiments which were really displayed in 1895 by Sir Jagdish Chandra Bose tells us that it is really a long journey of the millimeter waves, so many years after, but yet that particular invention has to be realized as a product, and it is yet to be done. So we are doing a lot of experiments in this domain, but there are a lot of groups around the world who are trying that, but the very short range, high data communication is very important. So similarly, so these all kind of anecdotes, they generally suggest that if you move up the frequencies, you're at a certain range from 500 to 10 gigahertz is fine. You can travel at least a 1800 megahertz or a 2100. You can make it travel from 6 kilometers to 10 kilometers. Lower the frequency, longer the distances, less number of cell towers. So it's quite win-win situation for the telecom service providers. For IoT, for home IoT, for certain applications in industrial IoT, we require to have a very short ranges within some specific domains. So they have a different radio propagation phenomena also, which deals with the fact that high data rate in a short distance. So people prefer to go for a little bit higher frequencies. But again, it has some difficulties in that particular domain, that there were a lot of attenuations and some propagation phenomena which are really worrisome, and that needs to be addressed. And a lot of research is going on in that domain. So whatever the energy is getting, when you really want to pick up as and transmit as EM sensors and radiators, the following equation that generally helps us to guide into the principle, that is the fundamental radiation equation. Now, whatever it tells us that the time changing current, the length of the current element equals the charge multiplied with the acceleration of the charges. So whenever there is a bending, if you have a straight long wire, a time harmonic voltage is used to excite the wire. So you may have a current, but the electrons are flowing with a uniform velocity. At that point, you may not have a radiation unless you make the wire too long. Those is called long wire antennas. But as soon as you start bend the wire, So there is a deceleration of electrons at the corner, and again if there is an acceleration. This phenomena generally helps in the entire radiation. Furthermore, you can go to the Krauss book for this fundamental aspect, which we generally should appreciate in understanding any radiating system. Obviously, we can go for the rearrangement of the Maxwell's equations, and we can link it to the radiated electric field with the source. So the source is a current carrying wire. There is a current density in a wire. There's a current density on the surface of a microstrip patch. So what will be the electric field? And for solving this expression, we require some boundary conditions to be evaluated, and then we can easily go for solving for the electric fields. Though they are more generic and routine solving, some cases we need to solve it in computers using numerical techniques. So you can easily verify that the electric fields which are getting emanated from this current distribution which is placed. So we can see that once it moves to the free space, the electric field forms a closed curve. It's because the divergence of electric field in the free space at the charge density is 0. So divergence of E is equal to 0. So therefore, electric field starts forming closed loops. So a loop of when it starts emanating, it forms a loop. That changing electric field will form a loop in the orthogonal plane for the magnetic fields. The changing magnetic fields will again produce an electric field. So therefore, a chain is created between the transmitter and the receiver. Very fundamental principles, but widely acceptable for each and every part of using it as radiators and also sensors. So I'd like to guide your attention to the science papers on the dipole, where it is these thoughts are very important. That is, the impedance, the resonance characteristics, and the quality factor are three important factors and parameters that need to be well evaluated for building up the antenna. Because that will be a guidance that how suitable it will be as a radiator or a sensor. Either way, it transmits EMS whenever your handsets, your wireless access point receivers, they have the same antenna which is also receiving the fields. So they are also getting a exciting, the current is excited because of the changing fields which are associated with the antenna system. So these three important parameters helps us to also realize the fact that they are circuit parameters. The impedance, the resonance characteristics, and the quality factor. Over the next few slides, we'll see that how we start evaluating them from fundamental principles, invoke very fundamental theories which we generally go for in our undergraduate courses, and how they can be brilliantly utilized in having a clear picture of the radiating systems. The first thing being, we generally teach within the second year the transmission line theory, EM theory and transmission lines. Distributed circuit theory, as we call it, for transmission line analysis was put forward by Lord Kelvin. Now his actual name was William Thomson. So William Thomson was actually credited and invited by AT&T to find out the faults in the undersea coaxial cable laid for the transatlantic communication, which Marconi was trying to solve as a wireless communication, and he was successful. So the wired connection, which is a coaxial cable under the sea, Atlantic seabed, obviously is a Herculean task, and AT&T had difficult times in finding where the fault is located. Then the ships can go and rectify the faults. So they roped in Lord Kelvin, and he also took on board, because of the contributions of Oliver Heaviside. He was a blind supporter of Maxwell electromagnetic theory, and he helped quite a lot in reducing the 21 equations which James Clerk Maxwell had proposed, because he was not knowing about the vectors and vector calculus. He was believer of quaternion convention, and he reduced it to the elegant set of equations which we generally read in the textbooks now. Though at that time the textbooks didn't mention, it was quite long, from the early 1900s. There were people who further accepted Maxwell's electromagnetic theory, and then they started teaching them in the university curricula, and it all went on with certain people really supporting the way it was getting shaped, the Maxwellian electromagnetic theory. Now, the concept of impedance, which was put forward by Oliver Heaviside, was really a very important milestone, for which we have the AC circuit theory. He initiated that. So Lord Kelvin roped in Oliver Heaviside, and both of them, they put forward the distributed circuit theory, which we also know as the transmission analysis and the transmission line theory. And this Selkunov expressed the impedance in terms of the resonant frequency. That was also a very important milestone, when we wanted to tell that, okay, the input impedance is not constant at all frequencies, it varies with the frequency. So therefore, this was some small steps which were shaping the entire RF circuit domain. And then came the reactance theorem by Ronald Foster. That is, the suscetance and the reactance slopes are positive for a passive lossless network. And invoking the Foster's reactance theorem in the resonator concept was by MacLean, who extended the Foster's reactance theorem for resonators. And therefore, you can find from here that the input impedance or the impedance, the resonance frequency of an radiator or the sensor, and the quality factor, obviously they will be governed by the insights provided by these people. And that shaped up the entire way we analyze the circuits. Though we can find a very wonderful relationship between the parameters which we intend to discuss, that is the circuit parameters in one hand side and the field quantities on the right hand side. These are the only two set of equations which elegantly link the circuit parameters in one side and the field parameters on the other side. So therefore, it also hints us and brings us enthusiasm that it can be that if we know the field quantities, we can predict the circuit parameters. And if we know the circuit parameters, we can evaluate very fast certain follow-up parameters which can help us in evaluating the circuit very easily. So I can quickly go through the widely accepted relation between input impedance of a transmission line, and we'll be using this concept for finding the input impedance of a transmission line of length L. This is how we generally represent it. It's important for the teaching pedagogy point of view. So we generally evolve, and for a lossless one, we can further simplify the tan hyperbolic to tan beta L, where alpha is 0. So naturally, we come up with a relation for the input impedance. So naturally, if we know the load impedance, what is the load impedance? So we can evaluate what is the input impedance. It's all well said when it is easy for us to calculate the load impedance and simplify that to find the input impedance. Maybe it is not every time very easy for us to calculate the load impedance. And in those cases, we'll see how we can evade those problems and invoke certain other methods of evaluating them. So it's a radiator which is connected to a feed line to a source, and we can find out what is the input impedance at the input terminal of the antenna. And this input reference plane, terminal plane, is called the input port of the antenna. The concept of terminal plane concept was earlier proposed, but over the years, microwave engineers, they made it a transition from the concepts of terminal port plane to the term getting widely used in such circuit design aspects is the term port. We call it port 1, port 2. Antenna is a single port device. So there may be traveling with antennas which may be having 2 ports. So when we try to build up the equivalent circuit, you may get it in most of the antenna textbooks. So we can segregate them into one which is the antenna impedance, antenna resistance, the radiation resistance, the loss resistances, and the other side we have the open circuit voltages, the generator impedance, the power incident on the antenna terminals, the reflected power, the antenna input power, and the total radiated power. So if you find the input impedance, you have to first identify what is the radiation resistance of an antenna. Similarly, you can go for a equivalent circuit of receiving antennas. One of the important aspects when we start determining from the equivalent circuit viewpoint, you can find the input impedance. So there may be a query that somehow we try to find the fields, the total energy which is stored in the electric field and the magnetic fields. That is from EM simulations which we have. Can we determine that? Okay, it's fine. We can also determine the input impedance. If you see the input impedance relation here, we very well utilize the amount of energy stored in the magnetic field and the electric field, and we can come up with a formulation which can provide you the input impedance, and we can split it up also. So there are certain books also which generally gives us this route of finding the input impedances and the input admittances. And when we do that, when we segregate the suscitance and the reactance, so we can have the privilege of finding the suscitance and the reactance slope, and which is positive for a lossless passive network, then we call it that it is following Foster's reactance theorem. If it is so, then we can have the suscitance and the reactance plotted such that it can alternately passes through poles and zeros. If you find the input impedance of a transmission line, you have found the input impedance, you will see tan beta L. So naturally, if you further simplify and find out the del X by del omega, you'll find that it is a 10 or a COT, depending on the short circuit, open circuit impedances. So it also passes. So these are special cases of such kind of an implication which we generally go through. But the initial aspects, so you can know how from the energy stored in electric field and magnetic field in the network, so we can calculate the suscitance and the reactance slopes and use it and then plot it such that the driving point reactance is an odd function of frequency. The principle can be extended to transmission line concepts also, and we can find out the poles and zeros. What are the implications then? We can find out that where it is resonant frequencies and where we are getting stop band frequencies. So what are the resonant frequencies of the circuit and where the transmission is zero? That is, we get a stop band at different frequencies. And these concepts, obviously, a short segment of a transmission line, which can be used to bound the electromagnetic wave, not transmit it. We can use it as a short section, which can be used as a resonator. It can be a lambda by 4 resonator, lambda by 80 resonator, lambda by 2 resonator. So that resonator can also be used, that resonator can be analyzed, and we can find that what will be the resonance frequency, whether that resonance frequency can be whether it is useful for radiating, or we can use that resonators, that particular frequency, as a transmission zero. That is, we don't use it, we can use it for as a stop band. We don't want to receive anything. And these aspects have a very important significance so far as correctly designing the resonator such that our final circuit implementation is near to the desired specification. And that's the reason we should go for such analysis. Though this analysis is for the particular cases like I just mentioned about the short circuit and open circuit cases. So we can find where the resonant frequencies can behave as a series resonance and for a parallel resonances. What will be the input impedance when it is less than lambda by 4 or less than lambda by 8? What will be the input impedance at lambda by 2? We can find out when we can characterize them by simply determining the input impedance. So we found out that we can either go for an equivalent circuit, find out the input impedance, plot it. It's a graphical way of plotting, find out the transmission poles and zeros. So series and parallel resonances can be identified. You can characterize the resonators such that you can find whether it will be radiating or it will be stopping those frequencies. It will be allowed to transmit those frequencies, pass those frequencies, or stop those frequencies, which is an important milestone in the design process. So the impedance concepts has led to the impedance formulations, which can be either gone to an equivalent circuit method, or we can determine the equivalent input impedance from the energy stored in electric field and the magnetic field. What are the power losses that you can calculate? We have a lot of EM simulators to do that. So in both the routes, you can find out the input impedance, and likewise, we can determine the resonance frequencies. Looking deeper into the Foster's representation. So when we deal with the equivalent circuits, it should be complete when we discuss about the Foster's representation of the transmission line resonators. For that, we can again invoke some kind of a generic transmission line segment. So equivalent Foster multiport network representation. To find an equivalent Foster representation from the admittance parameters, which can be calculated from the numerical field analysis, and we can have such kind of a calculations, which is for a short-circuited transmission line of length L, carrying impedance Z naught. So we can find the Z input impedance Z. We're not mentioning in Z in every time. So Z is equal to Zx, Z naught tan omega L by C. We can further rearrange that in the form of admittance Y, and we can define a frequency such that we can rearrange the expressions and then invoke meter-Leffler expansion for tan and cot, and then invoke that in the expression for Z to identify the different parts, whether what is the parallel resonance capacitances, what are the inductances, what are the fundamental resonances and the inductance associated with that, and the series inductances, series capacitances. So we can find out from this expansion of the input impedance relations with the invoking Mittag-Leffler expansion, that what are the different components which can help you to build up the equivalent circuit. And this equivalent circuit with the Foster's impedance representation of the first kind, where we can find the different resonances and come up with the parallel capacitance and parallel inductances. And then for the Foster's network representation of second kind. So you can see that most of the equivalent circuits can be generally represented in this form, and you can generally further evaluate them for using any circuit simulators for finding out the exact values and fine-tune the values. We can use other optimization, last mile optimization methods also to fine-tune the values. Similarly, this Foster's Nature's reactance theorem for antennas and radiation Q was also invoked, and we can find out, one can go through more in this particular paper. And they can further expand it. This was further expanded in the, we can see that this kind of representations for arbitrary lengths. And for that, we can also formulate it and find the reflection coefficient and generally determine the equivalent circuit network. So these are the generic ways of finding the equivalent circuit network, depending on what are the different frequencies, whether it is parallel resonances or series resonances or mix of both. So like a half-wave electric dipole, you can see the equivalent circuit representation of the series resonances. And for the parallel resonances, for the same, which is a slot, half wavelength slot radiator. So naturally, so we can determine the kind of radiator we are thinking of, the sensor we are thinking of, analyze the resonance characteristics by invoking the equivalent circuit formulations from the basics of transmission line theory and invoking Foster's reactance theorem in that. A quick computation will be that of half wavelength dipole, and we can find out that once you determine these values, so what should be the loss resistances and the antenna input impedance. So this one can easily compute from these values, and we can find the antenna current. So these are the, though we nowadays don't go for the analysis part of this, but we can easily find out that what's the implication of these currents on the overall radiation characteristics and find the loss power and the radiation power. These are generally obtained through the EM simulations also. So once you don't have an access to EM simulators, you can go for the equivalent circuit concepts and work out. You can further expand these two different kind of antenna systems, but there's a important note here that provided you have working with those kind of antenna radiators who use equivalent circuit, you can easily determine. If you cannot determine those, then you can break down into transmission line models. You can invoke ABCD matrices to analyze them, or we can go for EM simulators, and there are quite a few number of simulators which can help you to predict the equivalent circuit uh, data. The next stage, we go for the characterization part. That is, once you identify the resonance frequencies, the uh, re- resonance frequencies from the input impedances, we to further calculate the impedance characteristics. We are sure that the resonance characteristics they're matching. Then from there, the next level comes then a detailed characterization of the antenna parameters, which can be divided into two parts. One is the circuit parameters and the field parameters. So we can find out the input impedance, you can calculate them. Obviously, you come it in the form of the reflection coefficient versus frequency that you generally plot. The radiation resistance also you can plot it, and versus frequency. The VSWR, the obviously how much, once you find what is the input impedance, so you can calculate what is the reflected power. So how much power is the return power is lost. So that also you can find out the radiation efficiency and the impedance bandwidth. The impedance bandwidth is an implication from where we can find over what range it can be functional. It is true for whatever. Now, the fundamental aspects, like if you want to make it for Wi-Fi, you want to sense how much electric field is for the Wi-Fi frequencies to around 2.4, or if it is for the, you want to radiate in that particular frequencies for the home Wi-Fi network. So you need to cater to all the 14 bands. It is expanded to 2.467 to 2.487, from 2.412 to this 14 channels you must cover up. So when you go for this roughly 70 to 80 megahertz, so naturally you should plan that the entire radiator should be a little bit more than this to have some redundancy in your design. Because after final packaging, which we generally don't think of, but after final packaging, if the frequencies generally they get shifted also, they get the impedance bandwidth gets shrinked. So naturally, you can plan a priori that what should be the changes in the resonant frequencies once we go for the final packaging of the radiator. And that's the reason that you should keep it little redundancy in the entire design. Now, once you're damn sure that the circuit is working out fine at the correct frequencies, the matching is quite good, the matching circuit is designed, because one of the important part is the matching circuit plays a very important role in the detection of the RF signals. Now, a proper signal from the source, or you want to go for the director circuit, there should be a complete good matching network from the antenna input port to that particular circuit. So the matching network design is greatly influenced by the bandwidth over which it is getting designed and the input impedance, correct prediction of the input impedance for the radio systems. The other part is the field parameters, which we go for the radiation pattern is one of these. That how, if you see the different application need, like in the present, moving on to the 5G standalone systems. So we'll have the synchronized signal block, which is generally for registering the phones with the user equipment with the GNBs. So we require a wide, broad beamwidth. So one may tell that, okay, now omnidirectional antennas are gone, we have sectors. Fine, that's fine. 120-degree beamwidth is there. You put up the 120-degree beamwidth, that is also much required. But simultaneously, we moved on to user equipment guided frequencies with MIMO antenna systems and phased array concepts. So when you have a large number of array, so the beamwidth is obviously less. Now in the earlier domain, we wanted to increase the gain and narrow down the beamwidth with more number of sectors. So the requirement is go for an array. Now you have an array, but you require a broad beam from that array. That's the reverse need which has come up. We have a broad, we require a broad beam for transmitting the synchronous signal bus or the synchronous signal blocks for the non-access stratum. For that, we require a wide angle beam. But in the simultaneously, we are using antenna systems which are phased arrays, that is array antennas, whose obviously we have a high gain and a beam which is narrow. So therefore, the proper evaluation of the radiation characteristics like the pattern, the distribution of the power over the different points around the antenna in the far field domain, the directivity, gain, beam width, polarization, and obviously this entire thing is more important because we don't use either vertical or horizontal polarized. We use dual polarized antenna systems for most of this kind of cellular wireless communication systems for 5G and for 4G LTE onwards. So when you take dual polarized signals, so obviously it is quite a little bit more constrained to have such kind of radiators which can be compatible with such kind of systems. Now the concepts which are further down are the effective aperture. Obviously in certain applications we require the radar cross section. So if you have a more footprint, so obviously you can capture more amount of signal. So obviously very faint signal can be received. So the radiation efficiency is another entering term which you need to Ghatak do. We'll have some very typical ways in which we can have we can measure the radiation efficiency. And obviously, like the impedance bandwidth, the circuit may be matched to a certain range of frequencies. Similarly, not the entire band of frequencies in which is properly matched means that it will be radiating equally well in that particular frequency band. So therefore, the pattern bandwidth or the range of frequencies in which the pattern is suitable for a particular application may be 80% of the total impedance bandwidth. Like you designers may note that who are designing CP antennas, the impedance bandwidth may be much larger. Half the impedance bandwidth will be the bandwidth for the circular polarized bandwidth. The CP bandwidth will be nearly half to that. So having a wide CP bandwidth or covering the entire impedance bandwidth for the CP is a very challenging design point. In fact, antenna designers face these challenges till now even. There are different researchers, they provide different solutions, so that's a different way, but it's one of the constraints of the design domain. So when you take about the resonance characteristics, we generally try to find from the reflection coefficients. This is quite general. So here again, before moving on, we'd like to highlight the definition of the return loss, how much power is returned back, and whether we are plotting the return loss or we are plotting the S11 in dB. So generally what you get the outcome from the software for the S parameters versus frequency, that is S11 in dB versus frequency. It's not return loss. Loss cannot be negative. That's very true. So therefore, you should look for and be aware that when you're providing the specs of your own designs, don't mention it as a return loss versus frequency and then plot from 0, then -5, -10, -20, -25, and then go down to -60. So it's not about the return loss. It is S11 in dB. So this is a small thing which you should find out and keep track of. Now, when we look into the characteristics, now from these S parameters versus frequency, we generally can determine the range of frequencies in which the matching is acceptable. The reason for choosing this S11 dB as -10, the many parties at that, it corresponds to a VSWR 2. So in the Smith chart, you will find all the points within the VSWR 2 circle are acceptable and considered for impedance matching. So those all points from FL to FH will be lying within VSWR 2. So this is this range of frequencies where over which the antenna has a suitable performance so far as the input matching is concerned. For multi-band systems, you can repeat the same thing at multiple frequencies. They may be individually, they may be very narrow. So you can define it as a percentage of the center frequencies, F1 and F2. But though we find the ratio of the frequencies for fractional bandwidth measurement, but still it is this is not a hard and fast rule. You will find many wideband antennas being referred to as we got 110% of bandwidth. So mentioning it as 110% or 115% or 120% is something which is a catchy data. So generally they try to mention it, but truly the antenna parameters guidelines to provide it to be the fractional bandwidth, which is we want to define as a ratio. The next part is about the utilization of the different resonator. You are designing the antenna characteristics, you're finding you know what to design. The fundamental things is we went for defining the input impedance, the resonant frequencies, the quality factors determine the input impedance, resonances, everything is fine. That we know it. Now the resonator which you're analyzing, that can be used for different purposes. Let's see how. The square patch resonator, it's a very important where we can find from weak coupling that what's the resonance frequency. We get the peak of the S21 from here and follow the cursor, we can find the resonance frequency designed at 6 gigahertz. We can find the dimensions of the particular mode. We can use the same one to make a microwave crossover. We can use the same square patch resonator to make a Prof microstrip patch. So it depends on when you make a circuit, the build-up of the resonator, which is a fundamental concept. It's a fundamental building block of the circuit. Whether you make the impedance matching networks, you are adding some stubs. They're also short length of transmission lines. They're also acting the resonators. If you want to bring a stop band for that, see that the transmission 0 of that particular step matches to the stop band frequencies which one you intend to build up. So therefore, the design of the resonator is very, very crucial. So let us take a small example here. Now in this, we take an example for microstrip patch antenna on a substrate of a given height, the probe. So when we go for the input impedance resistances, we can find out the input resistance for a square patch. There has been some closed form relations which have been provided and invoke these edge impedance resistances from them. And we can determine that the edge resistances for such kind of a patch, rectangular patch, can be going from 100 to 300 ohm. So we can find out the position where it is matching with the probe fit, which can be a 50 ohm. So we generally choose a point X0, Y0 and give a probe fit there. There are this relation for the probe fit. This expression is quite helpful. But if you use the same for the inset fed, we don't get the desired results. And that's the reason we have been seeing that over the years there has been new formulations which have come up, which has helped in improving our assumption for determining the input resistance, where we can, to which depth we can cut through the patch and give the inset microstrip feed line. Now this is very interesting design where this is a part of a large phase arrays where these input feeding microstrip, they can be connected to phase shifters. So insert fit patches are quite uh, often used. But if you use the same relation which is there for the probe feed, you find the input resistance and using the edge resistances and go for probe feed formula, you will come up with the wrong result for input uh, impedance of a insert feed, because the only reason that you're cutting some part and moving inside. So naturally, it is reducing the amount of metal region there, so it's reducing the capacitance. So you need some corrective measures. So over the years, there have been new formulations, and finally, the formulation reported in the IEEE magazines in 2015 was generally uh, quite acceptable, which provided the best possible solution for determining the input resistances, where you find the input resistance for this final modified formula, because in this past 10 years, we didn't find any other new formula coming up and contradicting this particular result. And this particular formulation provided the best possible matching. So uh, it is really this particular thought came up from that people, when we are using the for phase arrays using insert fit patches, they should start with the fit formula and start doing some heat and trial and go for calculating, but without thinking that what is they're exactly doing, or the thing they're missing of some facts. And over the years, these particular thoughts that there has to be certain corrective terms which generally takes care of the amount of metal which has been taken off from this square patch in providing this space for the insect feed. Generally, these are the almost same as the feeding network, that same width can be used. So it's a quite a 3 times of WF. So that amount of region is cut off. So naturally, that will affect the overall capacitances. So when we go for the feeding network, so it's for these microstrip patches, we generally go for these corrective formulas for enhancing our design experiences. One can go for the final designs, find out the edge impedances, and then find the true plot. So this is the where the correct design of resonator plays a very important role in determining the input resistances, input impedances. So each and every step of design is very, very crucial. If you thought of the input impedance, you made the equivalent transmission line, it's fine. There are a lot of textbooks which go for determining the equivalent transmission model of a square patch. But when you're actually implementing it, so the kind of feeding network also plays an important role in providing you the correct estimate of the input resistances and the corresponding matching network. And obviously, the wrong design would also give a doubt in your mind that maybe it may be resonating in a different frequency, so I'm not getting a good dip in this one. So that means there may be some near frequencies, without considering the fact that the proper choice of the input resistance was not availed, because of which we generally didn't get a good dip in these parameters. So this fine tuning, they can move you away from the correct design also. So therefore, one should be very aware of the different design aspects and guidelines in choice of the resonators, the way we analyze the resonators, and the different segments in which we are, which we want to characterize the coupling between these resonators and the antenna systems also. So when we come to the regions around an antenna in characterizing the far field and the fields around, obviously the different regions are the reactive near field, the radiating near field, and the far field. So when you're using as a sensor, you can be in the far field, you can be in the radiating near field, it can be in the reactive near field. Like the reactive near field, it can be utilized for near field communication. So there's a separate segment where it is. So induced fields are possible. So when you're quite close, the sensor, you've brought it quite close to the area. But in various ambiences, particularly for harvesting purposes, you imagine you always take care of that. We are always there in the far field. We are picking up the far field. So What about those which are devices which are in the uh, radiating near field? So that is also has to be taken care of. So when you're making sensors, the proper evaluation at different zones, only mentioning the far field characteristics would not be very fruitful, in because you may miss the fact that you may have picked the radio tower, but a more power a signal strength of higher value, because if you take the user equipment, your handset, and check that what is the field receipt signal level from the nearby base station tower, it will be you getting minus 110 dBm. So you may be having a hotspot shared from your user equipment from other person, that can be also picked up by your receiving antenna, by the sensor, EM sensor, which can also pick up the thing which is quite close to the radiating system, which can be another uh, laptop very close to your user equipment, or the radiating systems which you have used for capturing that amount of energy. So we have to need a quite good set of measurements facilities for capturing this entire data. That is, what will be the different field strengths at different distances from the antenna systems. You can use network analyzers and spectrum analyzers to simultaneously find out the amount of signal received. These are quite generic. I hope you may be quite aware of the different radiation profiling, that is the main lobe, side lobes, and the back lobes. So you may have a directed beam towards a particular user equipment, trying to find out. And generally, you can switch that beam also to different user equipments to capture it. It can be just as a burst. It can be picking up some burst of signals from arriving from different user equipments. So that can be a scanning kind of a procedure which picks up. So you get to have a very precise, very narrow beam width for making such kind of a sweeping kind of an arrangement. So like we took up the basic radiator as a square patch which can be utilized. So here it's also the current distribution on a half wavelength dipole is shown, and how the magnetic fields are emanating from that particular time harmonic uh, current profile on that particular wire. So this is way we generally find out that how the it is, you see that once it is moving away, and it is once it is converging into. So that's in the receiving phase and also in the transmitting phase. So it can be sensing the magnetic fields around. It can be emanating the magnetic fields as a radiator. So there's the current induced as a vector diagram you can see, and in the vicinity of the radiator, how we can see that the fields are affected. So the proper calibration, these examples are there for the half wavelength dipole. You can easily visualize it for the radiators you're designing. One is able to design, and I think there are also lab sessions in this particular um, FDP, which is one of the components where you can also practice that how to do it with some openwares. This has been used. We have used CST student editions for this particular kind of simulations. So for more detailing, we can evaluate the E theta H phi, and from there you can find what the radiation intensity, and likewise find the directivity too. The next set where we generally come up is a specific kind of a domain where we want to discuss about the aperture, because it's the microstrip pads are kind of an aperture antenna. But when we are more precisely dealing with that, so we can invoke a sheet where aperture source in z is equal to 0 plane is created, And likewise, the radiated field from such an aperture is linked to a plane wave with vector amplitude A and the direction of the propagation vector K. So we can easily formulate the electric field in terms of the vector amplitudes, and then we can invoke to find with some Fourier transform what should be the values of the electric fields. Now, generally, the near field, the Fourier transform of the near field is the far field. That's where generally all the softwares they compute the far fields. They'll find what is the aperture field in the near, in the vicinity, and then they make it a Fourier transform of that, and that becomes a far field. So these transitions can be well versed. You can write some small Python codes to verify them, like what is the kind of an aperture, what should be the field far field distribution, and one can easily find that within this we can synthesize the radiation characteristics of different radiators. Like this is a case of an open waveguide, a short length of a waveguide. You have kept it open. So the T10 mode, you can visualize that it's an X-band waveguide. So it's just 6.57, a little bit more attention on this particular cutoff frequency we can find, which exactly matches with the data which is provided by various electronic industry association design guidelines. So there you can find that these particular waveguide, and if you find just in the vicinity of this aperture, this field has such kind of a variation. You can see the variation can be confirmed from the EM simulations which are in the just at the mouth of this particular aperture. You can confirm such kind of a cosine variation. I'm not going into these deep detailings. I will give some time for question answers. One can easily verify them and write some small codes. These can be some nice examples which you can use to give us examples in the simulation labs for the undergraduate students, and they can match the simulations with the field quantities they are observing. So maybe this particular waveguide as an aperture is not a good radiator, broad beamwidth, but it can be used very easily. Such kind of waveguide apertures are very prominent for very short range communication applications for very high frequencies. You need to require a big mouth, like we designed it for a horn. So if you can flare it, we can make it a horn antenna, but it is not required. We want to make it compact, because in this as a sensor also we don't require it to be having a very high gain. So sensing the electric fields will be quite easy for us in that respect. So we can have close home relations for finding the directivity for such kind of physical sizes of aperture. In terms of that, we can mention it. And if you have a flaring of that particular aperture, then we generally come up with a horn antenna, which has a higher gain and more directed beam pattern. So the beam width will be much narrow in this case. These are quite generic ways of proving that radiation characteristics in terms of the antenna efficiency and antenna gain is quite well known. This one point where one should express the realized gain, because the gain which you generally calculate from the measurements, you calculate the first match, what is the matching efficiency, you calculate what is the input reflection. So the reflection coefficient should come into the calculation for the gain, because the realized gain which will be provided in the spec, so which is the absolute gain into 1 minus mod gamma square. The other principle, which is a very important milestone, like of Babinett principle, invoking the Babinett principle in antenna systems, it tells us that the dipole, electric dipole, and the same length slot would have a same kind of a radiation characteristics. Only thing is that the reversal in the value of E theta and H. E theta will be the H theta for this. The electric fields will become the magnetic fields in case of this slot, and the magnetic fields in the and will become the electric fields in this case. So this reversal of the way in which it is radiating, that will be only occurring, but the radiation pattern will remain same. Only we will be replacing E with H, either of the cases. Another aspect which is we cannot overlook is the effective height of the receiving antenna, which is indirectly, which will be important for us in determining how efficient it would be as a sensor. So the effective height is the open circuit voltage, which is created across, and the electric field strength, which is increased upon that. And from here, we can also come up with another term, which is the antenna factor, both the electric and the magnetic antenna factor. We can express it in terms of the log scale also. And that is a very important term in determining that what will be the characterization, that is how much is the field strength or the magnetic field strength, electric field or the magnetic field strength to the received voltage. And that generally gives you, if you know the antenna factor, you know the field, you can find what is the received voltage. So you can just characterize that, how much is the voltage output. So that you can generally calculate. In determining the Q, we have the fundamental relations like the unloaded, the external circuit Q externals, and the loaded Q. So whenever it is just a simple resonator, what will be the unloaded Q? Though it's very important that whenever you use the resonators, it is coupled to a external circuit. So the external Q and the loaded Q play a very important role in determining that. We can also invoke the electric fields, energy stored in electric fields, and the magnetic field concepts can be invoked. That is, from the energy stored, we can invoke that, or we can go for an equivalent circuit network. We can do that. Once for the concept of radiation Q, one of the important and fundamental importance for the antenna designer is that this quantity has a practical importance in the bandwidth of the antenna, which is computed substituting the value of the Q. Now, the radiation sphere is a hypothetical sphere which is 1/3 the wavelength corresponding to the lowest resonant frequency of the antenna. Now, Maclean, he extended this work of these Qs into the lower limit of the antenna on the Q. That is how small the antenna can be. It was told that more the antenna can fill the space of this radiation sphere efficiently, it will be far better. So the radiation Q will be high. So we'll have a nice radiator. So there's a concept that we started from a dipole, and people started invoking fractal architectures because a fractal geometry would fill the space very efficiently. That's the reason that we went for a fractal designs in most of the past 2-3 decades have seen a wide acceptance of the fractal geometry for this purpose. Miniaturized, small antenna, but they are efficiently filling up. But the computation of Q was put forward as by Chu did not consider the reactive energy stored. Hansen and Collin, they introduced the modified Q formula, and this Chu's formula was upgraded as what you see in the screen, and the bandwidth of the antenna can be improved if and only if the antenna effectively fills the available volume within the sphere. So you'll have a wide band antenna. Also, it will be miniaturized also. So compact wide band antennas as in designed if it fills up the available space more efficiently. So this meandering structures were there. People went for meandering structures. People went for fractal geometries. So these were the way they looked at this particular problem. So the Hansen's and Collins paper also, you can have a collective collection of that. in understanding the radiation Q and its implication in the overall determination of the quality factor, and how what will be the bandwidth and how wide it can be for its overall application domain. And also one of the things is that relatively small antenna, if you move forward, so then also, then if you, how small it can be. So you make it electrically small antennas, but how small it can be. So that also has a definitive limit that we cannot achieve more electrically small antenna, which is violating the radiation cube concepts as put forward by Hansen and Bolling. Now, one aspect here was mentioned that they did not consider the reactive energy, stored in the hypothetical sphere. Now let us see how we can do that. That's also an important step, that how well we can go for the antenna efficiency measurement. I mentioned this part also in this initial part of our discussions, that the antenna efficiency, which is generally the radiation power by the input power. The radiation power and the input power consist of the radiation power plus the power loss. Both the parameters in the data can be easily obtained as a whole, but cannot be separated easily. Enclosing the antenna within a conducting sphere or a cylinder. Now, from the sphere, whose radius should be 1/3 of the lowest frequency, corresponding to the lowest frequency in which it is radiating over the wide range of frequencies, the lowest frequency. So the radiation, the cylinder of that radius equal to radiant length of lambda by 2 pi. And the radiation resistance would be eliminated from the input impedance without changing the loss resistances. So we can enclose, that is, we don't want the antenna to be radiating. We don't want the antenna to radiate, but all the power is confined within the region where it is in the reactive energy is there. So we can calculate the reactive energy stored very easily. Just cover the antenna. Here you see it is connected to the network analyzer. You find the input impedance. You have the antenna which is kept in free space, but the antenna, the ground plane is there. You have a wider ground plane. It is covering that ground plane. You consider the particular metallic cylinder. It can be a simple metallic container which can be used to go for this. Now, this metallic container is called the Wheeler cap. So this is a Wheeler cap method of measuring the antenna efficiency. So once you confine this metallic structure of how much radius? Lambda by 2 pi. So there you can confine it and find the antenna model using a series RLC. You can find the efficiency as you see in the left hand side. And for the antenna model as a parallel RLC, you can find that using the right hand side formula. In this, the input impedance of the antenna in free space, once you do the measurement without the Wheeler cap, the WC is the ZWC, the input impedance of the antenna with the Wheeler cap. The shape of the conducting cap is not critical. The cylinder, this can be a small tin can, a baby food can also, which can use in your lab. Take a large aluminum ground plane and then put the radiating system and then cover it with the particular ducting, and then you have a method of measuring with the network analyzer. The cap has to make good electrical contact. That's very certain. If you see that there is something, you don't have a fixed arrangement, you can have temporarily soldering of the outside conducting cap with the ground plane. You can solder it. It's not necessary to have the cap perfectly centered over the antenna. The room in which the measurement takes place could cause significant changes in the input impedance. So better in an enclosure, you just try to see there's no incoming other frequencies. So, and also the ambient noise is less. So make a appropriate environment for that.
Sir, sorry for interruption. Actually, just you need to finish within 8, and before that, many participants will ask some questions. So for that, we need some time also. So sir, can you wrap up, sir?
Okay. I'm just about to end. I just wanting to. It is 5 minutes to 8.
Okay, sir. Okay.
So now this can be also extrapolated to wideband efficiency measurements also. The reflection caused due to mismatch is ignored in this approach, and generally So you can extrapolate this into a measurement where you can use a S parameter, fully S parameter based measurement systems. So you can see that how the S parameters have been used efficiently for measuring the radiation efficiency. So this is the way we can use the S parameters from the network analysis to calculate them. I'm not talking about the disadvantages. These are the more on the standards or for definition of terms for antennas. So that you can find the standards 145 is 2013. It was just revision is it is a revised version for that which is in 1993. You can get it from the IEEE standards. If your institute is a member for that from Explore, you can get it. And some quick notes that antenna efficiency and the genius of IEEE standard for antenna terms. I'm not, for shortage of time, I'm not explicitly mentioning them. It is a quite interesting read if you're so much involved into antenna parameters and teaching them in your classes. So for a lighter note, you can go through them, that how much it is, terms are also contradicting itself. So Vonnik had put up this article, a very interesting read. So thank you.
Oh, so sir, thank you very much for your nice presentation. So now I will ask participants to raise your questions if you have any. Thank you.
Excuse me, sir.
Yeah.
Yes.
Sir, myself, Dr. Tarun Kumar Das. Sir, actually, I am working on Filtena. That is, that is in a single device, both the antenna and filter structure can be combined. So, sir, my query is to you how to cope up with the harmonics which are generated by the filter. Because in the microstrip structure, due to the distributive nature of the structure, harmonics are generated. So, sir, would you please highlight any technique or something so that I can ignore those or suppress those harmonics in filter design?
As you're mentioning about the harmonics, you can you're implementing a bandpass filter with the antenna.
Yes, sir. Yeah. Yes, sir.
So you can just couple a low pass filter, which will
But
eliminate higher harmonics.
sir, actually, if I cascade low pass filter, then probably the size of the antenna would also be increased. Filter, na?
That is not a very big issue nowadays, because if you want to integrate it as a SOC, or then you can have multi-layer structures also. No worry.
Oh, okay, sir. Okay, that may
But
be
aligning
understood.
which has to be proper. Aligning has to be taken care of.
Okay, sir. Okay, thank you so much, sir. Nice presentation, sir.
Thank
So
you.
any other participants? Do you have any questions?
Sir, I have a question.
Yeah.
Am I audible?
Yeah, please go ahead. Yeah, you are audible.
Sir, my question is a very basic question. I want to ask, who is the true inventor of wireless communication? Whether is Marconi or J.C. Bose?
That's a very interesting question. I would like to refer you to a book, History of Wireless Communication by Tapan K. Sarkar, Magdalena Salazar Palma, and the another author, I'm just forgetting his name. I once heard Professor Magdalena Salazar Palma's lecture in which she mentioned about Dr. Loomis as a dentist who is in 1865. There's a plague also. So it was a dentist who tried to have a wireless communication set up in 1865, but the commercialization of the wireless communication sector, the first communication, it's not about communication, the radiated fields getting received. It was the first microwave engineer, which IEEE has also recognized as Hertz, but it was commercialization of the wireless segment, which was by Marconi. But if you take the experiments were done quite early. One of the such recorded one, though you will find that most of these anecdotes are getting re-researched and found out by persons from history department. Okay. And in fact, in certain cases, the books are also getting like these about the equations about Maxwell. It's a very interesting fact that is how we knew about how many equations he wrote actually, and how elegantly we knew about the Maxwell Heaviside equation, which Einstein used to call it, because it's not only the 4 equations. We should tell the constitutive relations also with that. So similarly, it was the book of Bruce J. Hunt, who wrote the book, The Maxwellians. So that particular professor, Bruce J. Hunt, is a professor of history. So similarly, we cannot exactly say, but the last known book which mentions about Dr. Loomis is this particular book, History of Wireless Communication. Maybe further researchers in the coming years may find some other aspects that who were the first to do that.
Okay, sir. Thank you, sir. And sir, I have another question. So chain of EM wave is radiated in space. So how an E field make a closed loop in free space?
That's you find the Gauss law, divergence D is equal to how much? Rho V? Is it? So when the in free space are there any free charges? No.
No.
So when rho V is 0, so obviously divergence D is equal to 0.
Okay.
In fact, this should be mentioned while teaching in the class. And that's what I mentioned in the initial points, that this tutorial I found that it has to have some teaching pedagogical point of view also. It should be important.
Okay, sir. Thank you very much.
Thank you.
So, any other participants? Do you have any questions?
Yes, sir. I have one question.
Okay, go ahead.
Sir, while designing a multiband antenna or a broadband antenna, which type of structure is desirable? Whether it is fractal or slotted antenna, which is better?
There is no fixed answer for this. Whatever is useful for your specs would be suitable. Maybe one will be suitable, providing a good bandwidth but not a good pattern. But where you are getting a good pattern and the gain is acceptable over the range, that may not be a fractal geometry. So that may be a different geometry also. So it's not there cannot be a hard and fast answer for this.
Okay, sir. Thank you, sir.
So, any other participants? Do you have any questions?
Hello, sir.
Okay, go ahead.
Hello, sir. Am I audible to you? And
Yeah, you're audible.
sir, actually, the slide is very detailed and informative. Can we have a copy, a PDF copy of the slide in
Yes,
low
handout.
resolution?
Yes, I'll be sharing the handout.
Thank you, sir.
So I thank you all the participants for your participation in this session. So actually now, forcefully, we need to end up this session over here because immediately our session, the timing of our session 2 is 8 p.m. So thank you, Professor Ghatak, for your nice presentation.
Thank
So
you.
I
Yes,
okay,
Hello,
sir.
sir.
Thank you very much. So I am ending my session over here. Thank you.
Hello, sir.
Yeah.
Sir, actually, I can see in the image there are lots of queries. Like many people